Welcome back to Science Sizzle. Today, we're diving into one of the most famous experiments in quantum physics, the double-slit experiment. It's the one that blew everyone's mind by proving light can act as both a particle and a wave. And guess what? A team at MIT just pulled off the most ideal version of this experiment ever. And the results? Let's just say Einstein didn't have it quite right. Joining us today is Nobel laureate and MIT professor Wolfgang Ketterle, who led this groundbreaking study. Professor, welcome to the show.
Thank you. It's great to be here and to talk about this experiment. It's something every physics student learns about, and now we've been able to test it in a way that even Einstein and Bohr couldn't have imagined.
That's a big statement. So, for our listeners who haven't thought about the double-slit experiment since high school, give us a quick refresher. Why is it so important?
The double-slit experiment is at the heart of quantum mechanics. Over 200 years ago, it showed that light behaves like a wave because when you shine light through two slits, you get an interference pattern, bright and dark fringes, like ripples in a pond overlapping. But here's the twist. If you try to figure out which slit the light goes through, it stops behaving like a wave and acts like a particle. You never see both behaviors at the same time. That's quantum duality.
Right, the famous, it's a wave and a particle, but you can't catch it being both at once mystery. And Einstein had an issue with that, didn't he?
He did. In 1927, Einstein argued that if a photon, think of it as a particle of light, goes through one slit, it should give that slit a little push, like a bird rustling a leaf. He thought we could detect that push and still see the interference pattern, meaning you could observe both the wave and particle nature at once. Niels Bohr disagreed and used the uncertainty principle to argue that measuring the path destroys the wave pattern.
So what did your team do differently? What makes this the most ideal version ever?
We stripped the experiment down to its quantum essentials. Instead of slits in a screen, we used individual atoms as slits. We arranged more than 10,000 ultracold atoms, cooled to just above absolute zero, in a crystal-like lattice using laser light. Then, we sent in a very weak beam of light so that each atom scattered at most one photon.
Wait, you were doing this at the level of single photons and single atoms?
Exactly. That's why this is so precise. We could tune the fuzziness of each atom, meaning how well defined its position was. The fuzzier the atom, the more information it could record about the photon's path. And what we found completely agrees with quantum theory. The more you know about the particle's path, the less you see the interference pattern. You can't have both. Einstein's idea that you could was wrong.
So after almost 100 years, Bohr gets the last laugh?
You could say that. We confirmed that even in this ultra-pure, spring-free setup, the principle holds. As soon as you gain which path information, the wave pattern fades.
You mentioned springs. What's that about?
Einstein imagined slits suspended by springs, so a passing photon would jiggle the slit slightly. That's how you detect its path. In many descriptions, people think those springs matter. In our setup, we removed the equivalent of springs completely. We let the atoms float free in space for a tiny fraction of a second, and the result didn't change. What matters is not the springs, but the quantum correlations between photons and atoms.
This sounds like something out of science fiction. You're saying the only thing that matters is the fuzziness of the atom?
Exactly. The fuzzier the atom, the more uncertain its position, the more likely it records which slit the photon went through. And when that happens, you lose interference. It's quantum mechanics in its purest form.
And all this is happening as we celebrate the International Year of Quantum Science, 100 years after quantum mechanics was born. That's poetic.
It is, and it's exciting because these experiments not only honor that history, but also show how far technology has come. Einstein and Bohr would never have imagined we could manipulate single atoms and photons like this.
So the bottom line, light is still a wave and a particle, but you only get to see one face at a time.
That's right. Nature keeps some secrets locked away if you try to look too closely.
Professor Ketterle, this has been fascinating. Thank you for taking us inside one of the cleanest quantum experiments ever done.
Thank you for having me.
And to our listeners, if you think quantum mechanics couldn't surprise you anymore, think again. We'll be back next week with more mind-bending science on Science Sizzle.